Hello, this is Steve Park from Mechanical Engineering. Today, I'll introduce about the tracking and mapping algorithm of stereo event camera. So, event camera is briefly detects the brightness changes asynchronously. Look at the right side. The circle is rotating with a high speed. Using the standard event camera, the motion blur can happen in here. But when we use the event camera, you can see in the downside the event camera detects the events asynchronously. In the downside, you can see two camera. The left one is the event camera, and the right side has the standard camera, and you can see the difference. So each event EK is represented with the pixel coordinate UK and VK, and time TK, and polarity, which shows the brightness changes, +1 or -1. So for this project, I did stereo camera calibration and rectify time series generation. An event is really sparse and tricky to handle. So an idea of converting events to an image is often used, and time series is one kind of the images. So using the rectified time series, I extracted best picture and I did stereo matching from left to right. And then finally, I did semi-dense depth map generation. So using that time series, and then I generated a 3D map, but it did not work well. I will introduce later. And using the semi-dense map, I propose a tracking algorithm for stereo event camera. The open source, what I utilized is the calibration tool and time series generation code from the Hong Kong University. The best picture extractor code is from the ETH, but I have to convert many things from the original source code. And ideal camera tracking is partially inspired by the first paper. To introduce about the product, the name of the vendor is the Innovation. It has the event camera, frame output, and IMU, and it provides this black cable. It provides the multi-camera synchronization cable. So at first I have to calibrate the stereo camera. So each camera can be located arbitrarily, as you can see in the gray scale. So first, I have to calculate the intrinsic, and then thanks to intrinsic, I can calculate the extrinsic parameter. And then using the OpenCV function, I can compute the rectification transform so that I can rectify the gray scale to a yellow scale. And then using these numerical quantities, I can process online rectification. Yeah, so thanks to calibration, the distorted right side events can be converted to left side. So the next step is generating the rectified time series. So on event, you can look at the right side. An event is really asynchronous, and they have the microsecond temporal resolution. So to convert an event to an image, we use the time series corner. It looks like this one, and then record the event into each pixel. Uh, so this one has the value from 0 to 1. So to efficiently compute, we should scale it from 0 to 255. Well, but the most important feature in the time series is that pixels in TS are asynchronous, so we cannot directly use algorithms for standard plane cameras. That's why so many algorithms like the best picture or the Harris corner detection cannot directly adapt to event camera. So people think of new way to adapt those ideas, and this is the one of the idea. So the second paper converts the best picture for event camera. So look at the most right side. So each pixel represents kind of time. So within each circle, for example, look at the red line circle. The 5 pixels in here are the higher than the others. And the blue one, the radius of pixel 4, has the 6 pixels have the higher value than others. when they happen together, then the center of the circle, which is the black pixel, is considered as the best picture. And then I did the sum of square detection, like in the defining when I found the feature, then I can define a patch. Then I can calculate the sum of square distance, and the smallest patch is the matched point. So this one has the low computation burden. But at first, my plan was to track those features and then doing the camera trick and then solving the camera tracking problem. But here, yeah, but the problem is that the pixel in the time surface is getting decayed, and since this is not informative as camera, the SSD doesn't work well in here, and the number of features are getting really getting big or small. They really varies at the time and movement of the camera. So, I I modified my plan. So, and next, I generated semi-dense depth map generation. So most of pixels are black, but only the white pixels are processed. That's why I put the name semi. So disparity is found using the sum of square distance with every pixel within time threshold. And using these equations, I can reconstruct the 3D position. But the problem happens the depth parallax. Like as you can see in the video, you can see many walls. This is happened because a pixel mapped to many disparity. This is the reason. So at this point, I realized that I cannot simply decompose mapping and tracking when using event camera. So yeah, but so far it consumes a lot of time. So the last thing is left as an idea. So I propose an idea of camera tracking based on the nonlinear optimization. And the main idea is inspired by the figure in the first paper. The left one is the semi-dense depth map, and the right one is the inverse time surface, which is just a negative sign. So look at this figure. Assume this algorithm runs iteratively, and assume we know the camera position t-1 in here. And then since and then in here we have the distance vector to 3D point, and in the PT we have the time surface and semi-dense depth map here. And assuming that the camera moves at constant velocity, each pixel have a time delta t. So the camera position can be considered as the pt minus 1 plus v delta t. So the vector from the new camera position to 3D point is the d minus pt minus 1 plus v delta t. And and then my idea is to reproject this 3D point onto the 2D image. The reprojection, the 3x4 projection matrix P is defined by P KRT. The K is given from the camera calibration, and RT can be calculated from the V delta T. So applying the time series kernel, then our goal is to minimize the gap between the reproject 3D point and TS. Yeah, this is the objective function. So within every pixel which has the value, this objective function is try to minimize the gap between the 3D point and the 2D point in the time series. So I hope solving this one we can calculate the V, constant velocity V, and integrating the velocity, I think we can track the camera position. So in conclusion, an event is sparse and tricky to handle. So idea of converting events to an image is often used. And when computing 3D reconstruction, we must consider the motion of the camera. So in future work, I'll try to using camera tracking using the time surface and semi-dense depth map. Thanks for listening.